What I'm about to show us is a proof for the properties of logarithms. This is going to be less important, but I do just want to show us where these properties are derived from. If I have two logarithms, and notice they have the same base, well, let's rewrite this as an exponent. I have a base of a, power of x equals n. Same over here, I have a base of a, power of y equals n. Well, what I'm going to ask us to find is, find the product of n times n. Remember, n was a to the power of x. N was a to the power of y. Well, when I have a product of powers, think back to the very first day of class. All of our properties of logarithms are going to mirror our properties of exponents. If I had x to the fifth times x to the seventh, 5x's and 7 more, that gave me x to the 12th. This was when I added exponents. Product of powers. Well, product of powers, this is when I add exponents. X plus y. That's the operative operation that we're going to do in this problem to show where the formula is going to come from. Now, if I ignore that middle part, I'm back in exponential form, single exponent. Well, let's look at what if I were to put this back in logarithmic form. If I had a log base a, because that's what my base is, of n, then what I could say is it equals the exponent x plus y, right? Your exponent is your logarithm. Well, what was x? X was log base a of n. So what I could say is log base a of n equals log base a of n plus, what was y? Y was log base a of n. The moral of the story, this is what's called the product rule. The product rule for logarithms is what tells us if I have a product in my argument, I can split it up as a sum. This was a result of when I would add the exponents. Logarithms are exponents. All of our properties of logarithms are going to mirror the properties of exponents.